Hi everyone. Today we're going to talk about multiple logistic regression, continuing with our discussion of modeling a categorical or binary response variable. So specifically, we're going to talk about the multiple logistic regression model as a whole, which is extending the simple logistic regression model, but with multiple predictors now. We're going to talk about how to choose or select our optimal model, how to fit it using R, and interpreting model coefficient estimates that we get. And we're also going to talk about how to check the necessary assumptions for the multiple logistic regression model, and then how to conduct formal inference using hypothesis testing and constructing confidence intervals. Okay. So as a brief recap, we are familiar with how to model a quantitative response using several predictors using an approach such as multiple linear regression. But now again, we're considering this case where our response variable y is a binary or categorical response, where specifically we code it as y being equal to 0 or 1. And we're going to model this using several predictor variables. So the assumed or theoretical logistic regression model that we are using here is given by this equation, where we model the log odds as a linear combination of our x's, of our predictor variables. And so the relationship between this and y is that we have that pi is the probability that y equals 1, where y is our binary response. And if we solve using Euler's number E here to solve for pi, you would find through a lot of algebra that pi is equal to this quantity here, where it's e to the power of this whole summation here. And this is called the inverse Logit function. Okay. And so the pi over 1 minus pi term here is called the odds. So we are actually modeling the log odds, where it's log base e, as a linear combination of our predictor variables. So this is a little bit different than multiple linear regression, where we're just directly modeling the mean response. Now we're sort of modeling this log of the odds of success. So a little bit different form. And here we're assuming we have k number of predictors or explanatory variables. Okay. So the textbook calls this expression of the logistic model the Logit form of the logistic model. They also talked about how you can use, as I showed earlier, this probability form of the model. But I think that's not very common to think of the model in this way. Typically, people express it in terms of this logistic regression equation here. So we're going to stick with using this. Okay. And just to plot again what this looks like, if we're to plot this logistic function, so solving for pi, so it's actually the inverse Logit function here. We have pi on the y-axis, which is the probability of success, and on the x-axis we have what they call the linear predictor, the linear combination of the x's, where we have intercept plus each of the predictor variables times its corresponding regression coefficient. And so the larger this quantity is, the higher the probability of success, the more that probability gets closer and closer to 1. And similarly, the smaller it is, the more negative, the more the probability of success goes to 0. Okay, and so even though this curve itself is not linear, it's not a straight line, there is an implicit sort of linearity assumption in the logistic regression model that we're assuming here. So we're not assuming that pi is linearly related to the x's, but we are assuming that the log odds are linearly related to the x's. And so to check that assumption of that linear relationship, what we'll use are empirical Logit plots, which we saw briefly for simple logistic regression already. Now we just have an empirical Logit plot for each predictor. Okay. And if we have a nonlinear pattern in the empirical logit plots, this can help us inform us of potential transformations of the predictor variable that might be helpful. So unfortunately, we can't, for like multiple linear regression, sometimes we could do a transformation on the response value or the response variable. But we can't really do that here. Here we need to keep, for logistic regression, the response variable always needs to be binary, the zeros and ones. So the transformation can't be on the y, it can only be on the predictor variables now. But that's okay. The empirical logit plots can still help inform us of useful transformations that we might consider if necessary. And so to determine which transformation is suitable, the textbook had some sort of helpful hints about shortcuts for when to know what transformations to try. So they indicate that if the empirical logit plot is concave down, so if it has a second derivative that's negative, so that might look something like, I'll draw my axis plots here. Okay, concave down is something that has a second derivative that's negative. So it's something that if we had something like this, like a downward upside down U shape, that's concave down, okay? So then it says try powers less than 1. So transform your x to be something like, maybe set your new transformed x to be the original x to the 1/2 power. Okay, so that's a power less than 1. So that would be, for example, the same as the square root of x. Okay, so that's like the first example here of what that suggests. All right. So that was concave down. If we observe a case where it's concave up, we want to try powers greater than 1. So concave up is going to look something like, if the points are like this, where it's like a regular U shape. So where the derivative of the trend is increasing as we go. The derivative starts off negative and it steadily gets more and more positive until it hits 0, and then it's growing. So this is concave up. Second derivative is positive. And so in that case, we would consider transformations that are maybe bigger than 1. So typically like x squared instead of just x. These are guidelines, though, and don't always work. It's just a general approach that's worth trying. What you should do is replot the empirical logit plot after the transformation and see if you made it linear. Otherwise, you can't know for sure if it worked. So, and we'll look at an example of doing that. So if we recall this data set on survival of passengers of the Titanic, we considered modeling whether or not a passenger survived, which is our binary response, 1 for they survived, 0 for they died, using their age in years. So looking at if this linearity assumption is met, we plot the empirical logit plot here, and we see this U shape, I would say. This is certainly concave up. Okay. So if we try a squared transformation, like is implied from the textbook, that would work. So unfortunately, actually, it doesn't work. We want to see a linear trend in these points after the transformation. We now have h squared here, but that's still just not the case. So it's sort of a rule of thumb, but it doesn't always work. I just wanted to show. It doesn't mean we did anything wrong. It's just that doesn't always, it's not always the case. Okay. But that's okay. We can also consider a different data set here now that's on emails that are spam or not. So I'm going to print 7 rows from this data set. I just used this code to randomly select 7 rows. And so we have 3 variables here in this data set. where the last column is spam, an indicator for the email being spam or not. So that's going to be our binary response. And then we have two candidate predictors, max length and total length. Here, max length is representing the longest consecutive number of characters that are all caps. Okay, so if we had a word that was 10 characters and it was all caps and that was the longest word in the email, for example, this max length would be 10. So it's the longest consecutive number of capital letters found in the email. Total length, I believe, is the total number of capital characters in the email. Okay, so you can see it's always bigger than max length because we count words with consecutive capital letters and then also ones that are not consecutive and sum them all up for total length. Okay. So these are our two candidate predictors with the idea that an email that's spam will tend to have a lot more capital letters in it. You know, you've won, you're a giant big winner of $1 million. It's usually like in all caps if it's spam. So that's the idea here. So modeling this using a logistic regression model, using the GLM function in R, we get this model output. What we see is that max length appears to be an important predictor in modeling whether or not the email is spam. The p-value is very close to 0, whereas total length does not appear important after accounting for max length. So notably, similar to multiple linear regression here, we have that this is describing the importance of the variable after accounting for all other predictors. So it's not the case necessarily that total length is not important in predicting whether an email is spam or not. It's just that this p-value being large is indicating that after accounting for the max length, total length is not very important for predicting whether an email is spam or not. So this is sort of a key distinction because this can give very different results, especially if the predictor variables are correlated again. If we have that multicollinearity, which I've mentioned before, where we have correlated predictors, then that can cause weird things to happen with multiple predictors in the model. So I'll give one example of interpreting this, one of these regression coefficients, just for demonstration purposes. So, okay, so for logistic regression here, these are given on the log scale. These coefficients are representing changes on the log scale. So we say since, for example, let's interpret the coefficient for max length here. So since E you have to calculate what this is here. All right. I'm going to open up R to calculate what this is. R is my very powerful calculator here that I'm using today. And okay, so R says that's about 1.02. So since that's about 1.02, for every one character, for every one character longer, the max all caps word is. For every one character longer, the max all caps word is in an email. We expect the odds of the email being spam to multiply by about 1.02. So not very much. The odds won't change much multiplying by 1.02. In other words, the odds increase by about 2%. Okay. Oh, and important to add, so don't be like me and forget this, after or I should say holding the total length constant. I guess that's a little bit weird here because if the max length increases in total number, and it's involving capital letters as well. So if this increases, this total length would increase by 1 as well. So that's a little bit of a weird example here, but this interpretation still is the best. That's the best way to interpret it here. So since e to the 0.025 equals about 1.2, we say for every 1 character longer the max all caps word is in an email, we expect the odds of the email being spam to multiply by about 1.02, holding the other predictors constant. So all this phrasing is very particular. We need these words such as odds in there rather than probability. We can't say we expect the probability to multiply by this amount. That would not be correct. So odds is different than probability again. That's something I want to point out. And then the other thing is a common mistake is to say we expect the odds to increase by about 1.02, but that would imply a linear increase, just an additive effect. But it's important to say it's multiplying by about 1.02. Okay, so this effect for logistic regression is a multiplicative effect, they say. Okay, so that wording is very particular to say, again, multiply instead of just increase, and then also to mention that it's odds, not the probability of success. Okay, so that's an example of how to interpret one regression coefficient. Yeah, we'll interpret a intercept term here later. So for assessing the model here, let's suppose we fit this model. Now we want to check the linearity assumption using some empirical Logit plots. So we do one empirical Logit plot for each predictor. So here to start, we look at the max all capital lengths of this max length variable. And here we see there's certainly a positive trend. The longer the max all capital length, the more likely it is that the email is spam. But it's not looking very linear. This is a concave down sort of trend because we have the derivative is decreasing as we go. So the second derivative is negative. So this is concave down. And if we recall back to what the textbook suggested, even though their suggestion didn't work very well for the first time, it's concave down. So it says try powers less than 1. Okay. So concave down. So let's try powers less than 1 for max all capital length. So doing the square root, we see that plotting the empirical Logit plot now, it looks a little more linear, certainly improved, but I would say it's still not exactly a straight line. So potentially we can try some other transformations to see if they work better. And in particular, a log transformation actually of the predictor variable can be helpful when we have this concave down sort of shape. And so trying that, we get this very nice linear pattern in the empirical Logit plot here. So perfect. That's exactly what we wanted. So a log transformation appears super helpful here in better meeting the assumptions of this logistic regression model. And it's not just about the theoretical assumptions here. By doing this transformation, we get better predictions in the future actually as well. So it's very helpful to consider and know how to do transformations like this. For example, I was working with a data set where it was open-ended and we were given data on whether or not a viewer liked a title on Netflix. Okay. And we had different predictors like the number of titles that they've watched previously and stuff like that. And so I remember plotting the empirical Logit plot, and it looked like you would think just using the number of titles that the people watched previously, you could just throw that in the model and that's it. That's as good as you can do. But looking at the empirical Logit plot, I saw that I needed a log transformation made that relationship much more linear and was much better able to predict whether or not a viewer would like a Netflix title by considering a log transformation. So it can be really helpful in real life situations. So also this spam data set is a real data set, I believe. So I didn't make this up. So this is an actual thing. Now looking at the other predictor variable, we have this similar pattern again, where we have this sort of concave down shape. So total capital length. So this time, instead of trying that square root, we're just going to skip right away to the log transformation. And hey, yeah, it looks pretty good, pretty linear here. So it looks like the log transformation is helpful for that predictor as well. Okay. So now let's try fitting a model where we have both predictors log transformed instead. Okay. And we see that max length is still very important. So now it's log max length. And the total length actually is even less important, the log total length, after accounting for log max length. But that doesn't mean our model's worse. Again, it just means after accounting for the log max length, log total length is not super important. That's all that's telling us. Okay. So, but still, let's because the p-value is so large, let's just try to drop total length from the model and just have a model with log max length. Okay, we're going to look at that output. All right. So now when we do that, we have this model fit, and this seems like a pretty good model. So let's interpret now. I mentioned before you can interpret the intercept term. So here I'll interpret the intercept term for this fitted logistic model. Okay. So just like before, we have to exponentiate the estimate. Okay, so since this is, let's see what that is using R. Okay. Since e to the minus 3.3 is about that, which is the intercept term, the odds of, I'll say the estimated odds of an email being spam of an email with log Okay, so the intercept term corresponds to the predictor variable being 0. So here, that is log max length. So the estimated odds of an email with log max length equal to 0 being spam are about 0.036. Okay. So pretty low. The odds of the email being spam are very small if it has a log max length of 0. So, but that's not a very good interpretation, because it's like, what is log max length? So this would not be a good interpretation. What we should instead say is we want to interpret this not on the log scale. The statement's true, but it's just not very helpful interpretation. So the estimated odds of an email with a max length with a max length of 1 being spam are about 0.036. Okay. So I got it off the log scale. How did I do that? So the log of something being 0, the natural log of something being 0, means that that thing is 1. So in other words, maybe I'm saying this in a funny way. We know that e to the 1, okay, that's I'm sorry. We know that log of 1 is equal to 0, right? So we know log of 1 is equal to 0. So if the log max length equals 0, then max length equals 1. Okay? So we can interpret this intercept term without it needing to be on the log scale. So we're going to get rid of this top interpretation because it's bad. And we're going to say, since e to the minus 3.3 is about this, this is our interpretation. Okay. So again, a little bit more tedious with the interpretations for logistic regression, but the more we practice them, the more it'll become more natural and makes sense, I think. Okay. So moving on from interpreting the model output there, I just wanted to mention another important assumption for the model is this assumption of random outcome, not a deterministic thing. So one way the textbook described it is we have to think of the outcomes as being generated using like a spinner with probabilities given by a logistic equation. So what they're talking about is maybe you have like this little circle with like a spinner thing on it, and it's got like 2 colors on the circle, and you like flick the spinner, and then you see what proportion of the time it lands on red or what proportion of the time it lands on blue. That sort of like random probabilistic outcome that's still binary or categorical. Okay. We can't have, again, for example, what's the probability? I'm trying to think of a good example here. What's the probability that a day has snow or not, using the number of inches of snow that day as a predictor? So that's sort of like a deterministic thing, because if there's a greater than 0 number of inches of snow for a day, then we know for sure it snowed that day. So we can't model that. It sounds a little bit obvious and contrived, which it is, but so this is more of a, not super important assumption, but it is still necessary, I guess. Okay. More importantly is randomness or independence of the observations. So again, this is most commonly violated with like time series data, so time data that's related across time. So if you have measurements, say, again, continuing with the snow, whether it snows or not in a given day, if we record that each day, then observations closer in time are going to be more related. So those are potentially violated in terms of randomness or not. So just something to mention. And then next time, I think we'll start by picking up on model inference for this multiple logistic regression model, but we'll conclude with here for this video. Thanks.